just before we do go any further, the next thing I want to do is kind of talk about the network more generally, right? Because one thing that we're going to use, not KMS for, but the encryption behind this is also for HTTPS. Remember, so what is this particular version, or what does the S stand for?
Secured.
And what that means is, well, why don't you tell me if, what does that part do for us? What does it secure?
It encrypts the connection with an SSL certificate, so it can't be viewed by people that don't have the correct certificate to decrypt it.
Exactly. So that stuff in the middle is going to be encrypted, scrambled up, so that even if there were other machines in the middle between A and B, Alice and Bob, that would be on the internet, of course. None of them would be able to see what's on the inside of those envelopes going back and forth. That's a good way to think about that. So we think of these things as virtual envelopes as they're going through the internet. They might send them back to A to B. They may very well be identifiable information on the outside of those envelopes, like IP address you're going to, the destination, the source. But HTTPS makes sure that what's inside of the envelope is inside, okay, stays encrypted. So that even if some other machine in the middle intercepts one of those virtual envelopes, they can't understand what's inside of them. It's very much a good practice. You mentioned SSL and TLS. That's how it's done, okay? There's another protocol by which that handles precisely the job we just described. The thing that handles the encryption of HTTP traffic is, aka HTTPS, is the transport layer security. The most recent version of that is called TLS, which, funny enough, perhaps is another acronym for people still. Another thing that people may not have heard of, which is SSL, essentially just an early version of TLS, but this is the new and improved version of SSL, which is what most your browsers will accept and they will be using. Again, there is a fantastic video on Computer File that does a good job of explaining this, like how does your computer range with a server to start talking and expressing themselves in code. We, from the outside, don't see those in working so much, but what we do go about and notice is when we encrypt our traffic, well, it turns out that it relies again on our focus from last time of public key cryptography, and this principle that if with public key cryptography, with some asymmetric cryptography, gosh, tongue twister, both A and B, they both each had their own public and their own private key, and using that public and private key, you can then solve that chicken and the egg argument and actually communicate securely, even if you don't have that shared secret established beforehand. So with asymmetric cryptography, remember, asymmetric allows you to establish a secure connection even if you've never gone to a website before or you've never had an app before now. So what does that mean for our browser to be using TLS and thus HTTPS to communicate securely with a server? Well, our web server is in the story and have what we're going to call now a certificate. And a digital certificate really is just a proof, and you can think of this, at least for now, as just being your public key. Yeah, this is your public key to this key exchange that has been signed or verified by someone else. So that website that has a public key and a private key, and this private key, stays private. That's not going to be out there. But in this case, the web server, your load balancer, your EC2s, they've often been digitally signed by some third party, Route 53 amongst them, or certificate manager. But for now, let's assume that there are some bigger parties out there on the internet. These are just companies, really, companies that do this for a living. Or at least that we all, at least the browser manufacturers, the Googles and Microsoft, the Apples of the world, they all trust on our behalf. So again, they're the ones that are going to be signing off the legitimacy of these so-called certificates, which are technically of a type which are called X509. So if you're curious about the protocol being used, this is the standard format in which those certificates live. Any website you visit with a padlock and a symbol, you're able to inspect and see that public key. So if you just go off and see, why is it secure? Okay, well, because it's got a certificate, an X509 certificate. In this case, being on Amazon's own page, it's signed by themselves. They are a registrar in that sense. But using RSA, the algorithm we just talked about. So version 3. And notice you're going to find the public key there. Okie dokie. So these are pretty standard things. They might vary on issuer type, but this is just the format in which those certificates live. And this is what my browser goes and has a look at. You can think of a certificate really as just being a printed piece of paper with some interesting information about that, like the name of the website, how long it's valid for, also, but most importantly, that public key, which again, we said last time, thanks to asymmetric key encrypt, it's just going to be a really big number, with some letters and numbers thrown in there. And this number has some mathematical relationship with that private key as well. So there are a few big players out there, and these big companies, these certificate authorities, as we'll call them, let's have a look. If I find, well, let's go to Wikipedia, for example. Who are they signed off by? So they're signed off by Google in this case. Wikipedia is signed by Google. And the issuer here, Google Trust Services, but there's a couple of other big companies that are doing much the same thing. So you might have heard this phrase again of a certificate authority when the system comes up. So what's a certificate authority? Okay. So when you set up your own website, when you perhaps go off and do this, these people, these certificate authorities, these so-called CAs, are really just a collection of companies whose purpose in life is, again, to digitally sign those certificates. And the manufacturers, the browser manufacturers of the world, the Google Chromes, the Microsoft Edges and the like, they have gotten together and have included in their browsers, like Edge and Firefox and Safari, a list of the authorities that they trust. The idea is that if you trust Apple, if you trust Google, if you trust Mozilla, the discussion aside around that, or just if you trust your browser enough to use it, then by transitivity, you should then trust the certificate authorities that your browser in turn trusts. Okay? But what actually happens when you go off and visit a website? So basically, when you first go to a website, you download that certificate. Your browser will get that from the website, assuming, again, using HTTPS. Your browser calculates the hash value for that certificate by looking at certain fields within that, the 509, using a special hash function that produces a fixed representation of that certificate. Why does it do that? Because the next step is this, all right? You look at the certificate, you look at the signature, really, of that certificate. It uses the certificate authority who signed that certificate's public key. And again, it's going to use that CA's public key, the signature from that server certificate. It runs it through the algorithm here and then effectively just decrypting the signature with a public key. That should then produce the exact same hash value. So that is to say that if you go to Wikipedia, if you go to a server, some page, and it's presenting you with a certificate, and it says that certificate has been digitally signed by some form of authority here, your browser can use that certificate authority's public key to decrypt that signature. And then, by way of these hashes, which is to say, yeah, let's confirm or deny that, yes, that server certificate was actually signed by the certificate authority, by the CA. And again, if you trust Google, if you trust your Microsoft browser, if you trust Mozilla, another question in of itself, but if you do trust them, they in turn trust these certificate authorities. The presumption is that, you should trust your secure connection to that particular website that you're visiting. That's what makes that HTTPS secure. Now, with that being said, why does that keep you secure? Because mathematically, yes, you and I, as a humans, again, we're the potential weaknesses in the story, because there are many, many, many forms of attacks that try to exploit this. One of such an attack is called SSL stripping. So again, for historical reasons, SSL stripping, but now refers to TLS stripping. And what this does is it involves tricking the user, whoops, daisy, into thinking that you have a secure connection to a website. Then you might, not actually have an encrypted connection at all to that website, but your browser thinks it does. And worse yet, you might actually have an encrypted connection just to a third party, just to a machine in the middle, some machine in the middle, so to speak. The way that actually works is so that if you, for example, we're in the habit of still just typing out URLs like this one, like www.example.com. Or maybe you're in the habit of just typing in www.//example.com, enter into our browsers. More likely than not, though, we're just typing example.com into the browsers, enter into the browser. Well, in that URL bar, in your browser, you'd probably notice over time that even if you type in the most shortest phrase of those inputs, even as low as this, like example.com, that still gets converted into a longer URL, with the HTTP / colon, whack, whack, perhaps small characters as well. And that's because your browser is just trying to be helpful here, okay? Technically, if you want to go off and visit a website, you still need to use a URL. And a URL in this case, it should start with a protocol. Your protocol is going to be HTTP, HTTPS, maybe something else, but your browser is just trying to be helpful. It's going to fill in that information for you. So you don't actually have to type any of that stuff into your browser. It might first try HTTP just because it used to be this, or HTTPS even now. But the catch is that if you start your interaction with the web server with HTTP initially, that first step, that toe in the pool, that might be enough of an opportunity for a bad person to try something malicious with your packet of information that's being sent to the server. And maybe they might send you back a response that tricks you into, or ending up somewhere else altogether, perhaps their own website, their own honeypot. And so they might be really clever with, maybe they make you think that you have a secure connection to the original website, the one that you're trying to visit to. Again, what I mean by this, so that if you, inside your kind of virtual envelope, if you have a HTTP message that looks a bit like this one, okay, which is just saying, get me / the homepage of example.com. But suppose, again, for the sake of discussion, that you're not using HTTPS, you just typed in HTTP or nothing at all, you're just trusting your browser to go off and fill in that information for you. What might come back from the server is something that looks a bit like this. The server then might come back with a message that says, HTTP version 3 of which 307, and that's another status code. That actually means, I'm going to give you a chance to go maybe search for that if you can. We've had a 404, we've had a 200. Can you find out what 307 might mean? So what does that mean in this context? The status code.
Temporary redirect.
Yeah, redirecting. So the browser's way of saying, okay, well, actually, I want you to go off to this other URL instead. Take a detour. What location is it going off to? Well, perhaps this one right there. And the catch is, though, that if you're using HTTP, and therefore your request is unencrypted, and suppose that for this story, there's a machine in the middle, something in the middle there, waiting, listening for you to fall into the honeypot, it can actually catch that response, and then this is coming from that machine in the middle and not the actual website you're trying to go to. Why? Because, again, if A is trying to talk to B, and then you've got something in the middle, okay, A point, or let's say an eavesdropper in the middle, it can actually be Eve in the middle that's responding. So A thinks it's talking to B, but there's actually something in the middle which says it's B, but actually isn't, okay? The catch is, though, that this eavesdropper there, this machine in the middle is quite clever, because you can see right there. Again, they're suggesting that you should be redirected, put a status code 307. Odds are you and I are probably in the habit of at least making sure the browser stays secure, at least if you're using HTTPS URL, so you might think, phew, okay, everything is good that way. In transit, it's secure, but it's very, very subtle, okay? If I could just draw your attention to the actual URL, at least on the UK keyboard, like on this particular font, no longer example.com, but examp1.com. Again, a bit of a contrived example, but a very subtle attack, whereby the hacker in the story has sort of brought a domain name that's very similar looking to example.com, but with an L. Now they've used the number 1, so they've, thanks to fonts, maybe on some screens look so close to an L that are you really going to notice the difference? And the implication is that, the subtlety of this attack is that you may well have a perfectly well encrypted connection to a server, but it's not Bob's story in the server. Your connection is encrypted to this eavesdropper, this machine in the middle. So SSL stripping, TLS stripping, really refers to this kind of attack where you're sort of stripping out what would have been a HTTP redirection to the wrong place. Maybe you never even end up on HTTPS at all. The eavesdropper in the middle always keeps it HTTP. But at least at which point here, once you land on their own doorstep, you're vulnerable to other kind of phishing attacks too. So other things that might be enough to provide them information that's actually not legitimate. Okay. There are ways around this, and I don't think we don't need to know so much around. Well, worth knowing about this one though. So That is to say that you do have ways to prevent that attack from happening. Again, one, if you're a consumer, if you're a user on the internet, you could get in the habit of just typing out yourself HTTPS only, and then the domain name you want to visit. But I will concede again, that's going to get quite boring quite quickly. That is hands down the most paranoid solution to do here, because you know you'll always end up at HTTPS if I type that out every single time to my browser bar. Hopefully the website actually supports that protocol, but most websites nowadays do. That being said, if you're on the flip side of the story, and you're actually on the designer of the website, the business owner running the website, or you have control of the server, there's a few different things that you can do. And in fact, one such a thing is using a protocol called HSTS, which is to say that you can actually set up your server, your EC2, to provide hints to browsers to say, you know what they should always use, only use HTTPS when talking to a server. No matter what the human has decided, redirect them always through this protocol. And Hypertext Transfer Protocol, strict transfer, HSTS, mouthful, again, that has, so you as the administrator here of the server, you just configure your server to send an additional HTTP header, which insists that you have to use it. Which is again to say that one additional line of code there, that's one header inside those envelopes that just informs the server that we really just want to be strict about our TLS. We want to be using TLS. We insist on using it. The user must have HTTPS, nothing else. And again, so the server's telling the browser, assume that this is the case, that I want you to use security for at least 1 year. I think that's what that is. So the number of seconds in a year. Okay, and that's really just a long time to the browser that, yeah, I'm actually going to keep my security on for at least a year. Should be the case anyway. Okay, but you can further, you can do, you can even change that as well to longer, to also include subdomains as well. Okay. Now, I did want to talk about one more thing, which is, I actually did have some examples set up. So let me just go over to this. Yeah. Trust this making sense so far, folks, yeah? One thing that we're going to get into now is really just, I guess, the discussion of what we want to keep off our system, which ultimately is just malware, right? I dare say malware is probably one of the biggest threats out there, just generally. So malware or bad software, malicious software, just something that someone's written that can do malicious things with it. That's the nature of software. Even if you've never programmed before, it turns out that it's not that hard to write a program, and that program could just run and delete all your files on your computer, okay? Or maybe just starts spending out spam, or just starts mining Bitcoin, anything else. So software, if you can think of it, software can do it. And whether it's malicious or not really is up to the person that designed or wrote the program to begin with. So you may have heard of types of malware, for instance, like a virus. And a virus is a piece of software that attaches itself to a host, just like the human physical, like the real world. Okay, so the virus is going to attach itself to a digital host that the human would have to do something in order to get infected, and you would have to, in a computer sense, open a file that's infected with the virus, start running on your computer, start loading into your computer's memory or your CPU. You have to click on an attachment on a link that's perhaps infected, and so viruses actually do require some human intervention, something from you to begin with, and human mistakes. So you're exposing yourself unintentionally to a piece of software that once in can do anything, and it can literally do anything that piece of software can, right? So it can delete all your files, it can send out spam, it can start whatever, it can email all your files to your other people. Once you have a piece of software running on your computer, all better off. So you might wonder then, okay, well, what's the line between, say, a virus or Microsoft Word or Spotify or something else that you might have installed on your computer? Really, honestly, hands down, ethics. That's it. That's the real line that we're drawn. Ultimately, like, we are then trusting Microsoft Word, we're trusting Spotify, we're trusting AWS really on anything that we might install on our own computer. We're just trusting that they're not doing bad things. Okay, because very often, once you have a piece of software on your computer, it technically can do anything on your OS, on Windows or Mac OS, whatever. It can make possible. Again, thanks to those manufacturers, it's really just a code of ethics. It really is just perhaps capitalistic pressures that make sure that companies aren't necessarily doing bad things and software that's doing bad things. Why? Because it's bad for business, if nothing else. If they're caught doing something bad, it's not going to be good. But with that said, like historically, it's quite possible for software to be written in a way, even within the constraints of the operating system that does bad things. Heck, like maybe it's accidental, like it can happen. There's a lot of stories kind of in the I love you bug was probably the most known one. Absolutely has been the case where, the I love you virus. This was around in the 2000s, the early days of this, where this would sometimes delete things. It was sending emails off to other people because a human basically was curious to see how it worked, okay? Now, with this said, like, the world is gradually getting better and better and better at designing better operating systems and the like that tries to sandbox things, virtual machines and the like. So your phone, for example, your Android, your iPhone, whatever, it's very, very, very good at this. Folks, you realize that your phone is just running containers. That's what is actually happening. It's just a virtual machine. Like, your phone's not real. It's just good at something, like, you'll notice that nowadays your phone is very constraining, is the right word? Because maybe sometimes annoyingly, apps can't do anything on your phone without your explicit permission. Like you, just phones containerize apps. That's why they run so quickly. That's why they're just able to get going quickly, okay? Yeah, and that's how you're protecting yourself from the underlying stuff. So you and I might not give much thought to say, like, okay, all the things that do come up on screen now, because we just want the software to do its thing. But more so than the operating system, you and I are increasingly now being allowed to weigh in on those choices on whether some piece of software can use a network, can turn on the camera, can use a microphone, can access your files and so on. So we're getting more building blocks, thankfully, to try to mitigate some of those concerns. But there are still viruses out there in the world, and in cloud, you can, all better off, you can be infected by some file you downloaded or some email or just bad access more generally. Or more worrisome than that, actually, if it's hands off, there is another kind of threat or malware, which is called a worm, and this is very similar to a spirit to a virus, in the fact that it's just malicious software. Again, it can do anything, but these things travel from computer to computer, often like at a lower level, without your interaction necessarily. So a worm, theoretically, once it's on your machine, once having affected it, once it's running, well, it could do that technique called port scanning, from before, when with maybe you can use that infected computer's internet connection and just start scanning the local network or the broader network, even the VPC perhaps, of other EC2s in your VPC, and see what's out there, Oh, I'm just seeing chat coming through. Yeah, so if one of those computer ports happens to be listening, and for, again, unfortunate reasons, the computer's not using encryption, you're not using security groups, you're not using authentication, it's vulnerable somehow, theoretically that worm can travel from machine to machine and making those network connections via those IP addressing. So yeah, that's one of those things that can happen. The downside really is that beyond just wreaking havoc in your own machine, your own virtual machine, deleting your files, possibly spamming people, mining Bitcoin, what's actually happening is that adversaries have been increasingly over the years just creating botnets, so to speak. Now it turns out it's actually much more valuable to a bad person to not completely disable your computer, because that doesn't really necessarily serve them in the long run, but maybe they want to install some software on your machine, on your EC2s, that's constantly running. So it might not be doing anything bad to you. Okay, none of your files might be deleted, no spam might be sent, but you are infected, you are part of this, you are being puppeteered because there is some piece of software constantly running in your computer, put in by someone else, okay? And maybe that backdoor has somehow figured out not just to infect your computer, but my computer and your computer and everyone else's computer here, hundreds and thousands of other machines in the world. And now if that software is smart enough and constantly listening for commands like a sleeper agent would, an attacker might send off some kind of attack, a command, not unlike those virtual envelopes already, just to this entire botnet of computers and say, okay, rise computers, everyone at the same time, let's all attack that one server. Let's everyone at once start sending emails, and everyone at this moment start mining Bitcoin. Everyone at this moment start doing something. You can actually use economies of scale in this case, using the network of hundreds, if not thousands, of computers all at once, and just have a much more powerful attack all at once. Okay. What formally those attacks have is what we're going to call a denial of service attack, a DOS, which is exactly what the name suggests. So sometimes an adversary's goal is just to deny the service to everyone else. Again, for political reasons, for financial reasons, the like. It's one thing for me on my phone, on my laptop, just to visit. I'm a bit annoyed at Google today. I go to google.com, I keep hitting reload. If I'm trying to deny a service to other people, but realistically, Google has way more resources than I do. So a denial of service only really works if you have more resources than the actual, than the site that you're attacking. But with a botnet, when you control multiple computers, you can actually wage a distributed denial of service, a DDoS attack, whereby, again, you send a command to this whole network of infected machines, and you say, all right, everyone, all at once, go to Google right now, hit reload. And when it's hundreds and thousands of millions of machines doing it all at once, maybe not someone as big as Google, but maybe a small business perhaps, that they're annoyed at or perhaps competing with, you can, via a distributed denial of service, try to deny the service to some actual customers, real users of the website. Why? Because, again, computer, long story short, it only has so much memory. You have a finite amount of resources. You can only do so much per unit of time. And again, if you completely distract a server or a machine by all those requests that are bogus, then the good requests that are coming from actual good users, real customers of the story, they can't necessarily squeeze in anymore. So you are denying service to the people because you're in the door, and it's distributed. That's really the difficult thing about it, because once a company figures this out, what's happening, hey, you're in the door, get out, like Google or Microsoft, they could clearly just block your particular IP address. They could firewall you out, for example, coming from my phone or my laptop or any of the device. Once they know where the attack is coming from, they can just deny or they can block that service right there and then. But if it's distributed, if it's a distributed denial of service that is distributed across hundreds of thousands of people, thousands of IP addresses, then that gets a lot harder to do. I mean, technically, yes, you could just block all the IP addresses of thousands of them, thousands of IPs, but very often you and I, we're going to share IP addresses too. Because again, if we're in the same Wi-Fi network, we're in the same corporate network, even though locally we might have a unique private IP address, to the outside world, we might all share one public IP address, for a whole company. So at some point, it's not just going to be Google's best interest to do that. They're not going to try to block all those IP addresses because we might end up actually denying service to good actual people, at the company or the same Wi-Fi network that just happen to be on the same Wi-Fi network as the attacker or this infected machine. And so that is really the value of attacking computers nowadays. It's not just one thing to get your computer individually. It's what your computer represents too. You are a node. You are an ally of perhaps a network of systems. So it is really just as well that we try to keep this kind of software out altogether with antivirus and the like. One such a thing that I would like to talk to is, well, what are we going to do in the cloud is there are some techniques that we're going to see in WAF in a minute, just for stopping them, kind of averting them when they are detected, which is, first of all, this idea of firewalling. Again, so our natural defense against this is just only allowing particular types of requests through. So that's one technique, but again, that is a problem at scale. Another technique is something called sinkholing, which is exactly what you probably think it is. Okay, so a sinkhole, as you can probably think of as being like a hole in the ground that just swallows everything up. And a sinkhole in this context is just a big black hole essentially for our data to go through. That is going to swallow up every single request and just not allow anything out. It's like a black hole, which again would stop the denial of service attack because it's just soaking up all the requests and basically throwing them out into the void. They won't actually take down the website of the company that's being attacked, so that's a good thing. But it's also going to swallow. It's also not going to allow any good legitimate traffic coming through. So that might be a bad thing. It's hard to disambiguate when everything looks like the same on the outside. Okay. So a sinkhole is basically just going to take all that traffic and just throw them out to the trash. Finally, another technique we could use is something called packet analysis. So I talked about this yesterday, if you were with me, at the OSI level. So we've got the OSI network that's broken up to 7 kind of distinct layers of the network. I talked a lot yesterday about layer 1 and level 2. Well, if you look at them at the application layer, so that's level 7, application load balancers and network load balancers, application load balancers, you could, at that level, start to think about the packets more. So again, so HTTP, we know requests via the web, yeah? We learn a bit about them, that they have these things called headers. Headers are going to be packaged along inside those packets, whereby, where the request originated from, your source, as well where it's going to, your destination. And there's a whole bunch of other metadata as well going on. And, what kind of browser are you using? Something called the user agents. What kind of operating system perhaps are you using? And where to your IP address? Sort of in like a geographical generalization. Are they in this part of the world? Are they in that part of the world? And so on. So instead of you deciding to restrict traffic via specific ports only, via just a security group, because that's not going to be helpful in stopping a DDoS attack, we could say allow all traffic to come through, but put them under a microscope as they come in, okay? So, for example, most of the traffic on the internet, say we're expecting it to come from Europe, okay? And then all of a sudden, we're getting a lot of traffic from IP addresses that seem to be based in North Korea, okay? They just, as part of their packets, information that says coming from Pyongyang, okay? Or they're from some other part of the world. So, just as long as they're from a place that we didn't expect, we can decide, and after having a quick look at Amazon how we can do that, just from analyzing those particular headers, that I'm not going to accept any packets from that location. The ones that match the locations I'm expecting, I'll let through. But again, that might prevent certain customers from getting through, certain legitimate customers who actually happen to be based in that part of the world. But in general, that's going to block most of the ongoing traffic. DDoS attacks are really frustrating because they can do a lot of damage. Usually until the resources of the company will eventually, especially the cloud-based too, if they rely a lot of auto-scaling and load balancing to help them scale up, usually the resources of the company are being attacked. They're going to hit where it hurts, which is your wallet. Just at a point as to eventually overwhelm and stop the attacker, yeah, who actually has a much more limited set of resources to begin with. But yeah. So let's think a little bit about the types of attacks we can use. So we've talked about HTTPS a moment ago when we talked about firewalling. I've used VPN as well. That can help where I'm sort of extending my corporate network outwards. That's going to be helpful that's going to be useful to extend my network, really just to pretend like this network is sort of part of it initially. There are some constraints around this, and we actually do have a little bit of a discussion around that in a second. But I'm not going to put that off as a way to block legitimate traffic in as much as just a way for me to access it from afar. I would need to install some kind of client, some client application really, just to act and behave as if I were part of this larger network. This is really all that a VPN is. It's virtually private. It's still going over the, scary internet, the World Wide Web, and all that does is just the effects of the illusion of, encrypting. So on either end of that tunnel, so to speak, there is going to be plain text coming through, and then this is ciphertext all the way throughout, and then plain text all the way. That's what makes HTTPS secure. It's also what makes VPN secure as well, is that you are encrypting. It seems that often encryption is our basic building block in almost every solution. Whether that's with or without a VPN, you're still performing encryption. That's the only real defense we have against this. It does boil down to that. To look at that in more detail, so let's imagine HTTP, whether that's VPN or otherwise, like VPN is really just the carrier, should we say? But what you decide to do within that VPN, whether that's SSH, whether that's HTTP, whether it's some other protocol entirely, let's imagine HTTP, that's how hypertext or web pages are going to be transmitted over the internet. If I'm a client, if I make requests to you for some HTML content to load a web page, then you as a server, as an EC2, would send the response back to me, and I would be able to see the page I just asked for, okay? That's how it would work. So, as an identifier, like just how format the request, but it's unencrypted, right? HTTP. So if you think about when you make a request to a server, if we're on the client here, we're making a request to the server on the right, it might go something like this, where because the odds are pretty low that if we're making a request, we're so close to the server that it would just serve the request to us straight away. It wouldn't have to hop through any of the gateways, any of the routers. Remember, these routers on the internet, the purpose of a router is just to route and send traffic off in the right direction. So they might contain a table of information that says, oh, well, if I'm making a request to some server over there, then the best path is over this way. Okay, I'll send it over this way, and then it'll send it onwards. It's called an autonomous system network. The job of a router, your home router, is to optimize and find the best path for the request as it goes through. So again, if I'm initiating a request as a client off to the server, I'm first going to go through router A, which is going to say, okay, well, I need to move it closer to the server. So it receives a request, goes through to B, goes through to C, eventually route to C, perhaps so close enough that it just hands over the request directly. The server's going to go and get the request, read it as HTTP, look at the other metadata as well of the request and see if there's anything else that should be asked for, and it's going to go and send the information right back as a response. So I'm going to have to go back exactly the same chain of routers, but back in reverse. But in reality, like, that might be different. It might not go through the exact same 3 routers in this example, because the internet's full of variability. So it might actually go from C to A to B or back to A, depending on the traffic and what's happening on the network. It's like Google Maps. You could take all sorts away. How congested things are, whether or not there might be a new path or, that is better in that amount of time. But remember, so with HTTP, unencrypted, plain over-the-air communication, like, it's not that difficult for a non-secure network using an unsecure protocol to read literally the contents of the packets going through and from. Okay, that's a vulnerability right there. And any of them can be compromised. So for example, here router A, which we said was going to be infected by malware, and a router is just a computer as well. It's just a bit of, it's hardware with software on it. So perhaps it was infected on purpose with like a worm, will eventually make it part of some botnet, and then it'll eventually just start spanning some server somewhere. So router A then is compromised in such a way that the adversary can then read all the traffic that flows through, perform SSL stripping. Again, we're sending all of our traffic through in an unencrypted fashion. We have another security loophole to deal with. So HTTPS is kind of our solution for this. And again, we've talked about this a lot. Okay, just to look at a couple of examples of things we might want to consider. I'm showing you this in more detail because you're about to do a lab based on these rules, okay? So what kind of attacks might surface when you're thinking about the internet? Think about your network now. One of these ideas is that of a cross-site scripting attack, XSS, and this is, when we discuss this idea between server-side code and client-side code. If you're running something on the client-side code, again, that's something that's going to be running locally on your computer, your browser, for example. That's going to be expected to interpret and execute that code. But if it's running server-side, then that's running on a server. Okay, so when we get the information from a server, we're not getting actual lines of code back. We're getting part of the outputs that the code, having run in the first place on the server, spits out. So there might be some code on the server there, some Python, some PHP or whatever, that generates some HTML for us, the actual output of which is going to be server-side code. We don't actually ever see that code, okay? We only see the output of that. And a cross-site scripts vulnerability exists where a bad person is able to trick your client's browser to run something locally, to run something on your machine, and it will do so presumably, the person, the client, didn't actually intend to do. So bear with me, again, this is just an example of a very, very simple web server called, this is using a web framework called Flask for Python. So we have some Python code, and again, don't worry if this doesn't make a lot of sense to you. It's pretty short, it's pretty standard stuff for a web server that does two things, okay? So this is just some boilerplating going on in Flask. Flask is a package of Python that's going to be used for web servers. All throughout the course, we talk about Apache, Apache web server, HTTPS web server, but this is one alternative there, okay, where this web server, if you want to get more kind of control under it, does two things. The first thing is that when I visit this slash there, so let's say this is my website, okay? If I go to market.com, which you may not actually explicitly type anymore, but most browsers already do, okay? But slash just means go to the root, go to the homepage of that server, okay? So I'm going to call the following function, whose name happens to be index in this case, okay? Just return hello world. So that basically means go to market.com / or whatever.com / and then what I received back was just the HTML page whose content simply says hello world. Okay, and again, this code here is all server-side code. You don't actually see this code. You just see the outputs of that code, okay? You just see, which is in this case, just HTML, simple string in this case, but it would be interpreted as the browser as HTML. However, I get a 404 down below. So Richard pointed out 307 was a redirect. 404 is a not found error. It means that if I ever go to the page I requested and it doesn't exist, and since I've only defined the behavior as literally one page, slash the index page of my server, then if I want to call this function here not found, so return not found plus the whatever page you're trying to visit, okay? So basically, this is another simple web page, which much like the hello world from above, instead of saying hello world, it just says not found, okay? And really just concentrates on the very end of whatever page you just tried to visit, okay? I'm setting this up, I'm doing a bit of table setting because this is a major cross-site scripting vulnerability. To understand why, let's imagine if I go to another page on my website called foo. So let's go to market.com / foo. Okay, foo and bar are often like techie terms for this. So with our error handling function, okay, which I've reproduced down here, so that's going to return not only foo, it's going to return not found plus / foo. Pretty reasonable, okay? It seems like the kind of behavior I would expect or I would have intended to have happen in that case. But what if I go to another page like this one? What if instead I so I literally go to the browser, if I type in, that's way too big. So market.com / and then script. I can't type it with my hand. Okay, alert, hi, or whatever it is, close script. So this script looks a lot like HTML. And in fact, when the browser sees this, it will interpret that as HTML. So I'll get returned by visiting the web page and not found and then everything here, except for this leading slash. Yeah, this means that when I receive this and my client is interpreting HTML, I'm going to generate an alert. Okay, well, what's an alert? An alert, again, if you've ever gone to a website before and you had like a pop-up display some information, like you have to click OK or like X to make it go away, that's what an alert is. JavaScript treats a pop-up as an alert, which is when I visit when I go to a website, I've actually tricked my browser into giving me a JavaScript alert, or I've tricked whoever visits my webpage to give a JavaScript alert. And that's probably not exactly a good thing, but I can get a bit more nefarious than that because let's imagine, instead of this having to be on my server, okay, it might be easy to imagine if it were like this. This is what I wrote, okay, the script tag up here. So this is what I would write into my social media handle, okay, my profile, for example. So, social media will allow you to have like a little short bio about yourself. You can talk about yourself. Let's imagine that my bio was a script here. So documents.write, okay, and then I have this hacker URL and everything else down below. Okay, so imagine that I own hacker URL. That's my web page. That's my own IP address. So I own hacker URL, and I wrote this kind of profile that I get people to click on. So assuming that the page doesn't defend against this, and we'll see how you can do this in the cloud. If you don't defend against cross-scripting site attacks, which you would do, but assuming that they don't, anytime someone visits a page like this or clicks on that, your browser will be forced to contend with a script tag here. Why? Again, because they're trying to visit your web page, they're trying to get onto your social media site or something. It literally contains these characters which are going to be interpreted as if they were HTML. So it's going to add document.write. Again, that's a JavaScript way of saying add the following line in addition to the HTML at the bottom. So source image, as if it were HTML, and then cookie equals document.cookie. So imagine that I, again, control, that's my URL, hacker URL, I own this. Presumably, I'm someone that runs a website. I also maintain logs of anyone that tries to visit or access my website. Well, what page on my site they're going to try and visit, okay? So I know that if someone goes to my profile, and if they execute this on their computer, I'm going to get notified on my URL, on my hacker URL, presumably that someone has tried to go to that web page, query cookie equals, and then document.cookie. Okay, now document cookie in this case, because that exists on my profile, like that's your individual cookies for the website that you're trying to visit. Okay, so here what I'm doing again, like if you didn't defend against cross-scripting site attacks, assuming that, you know, what I'm doing is I'm being told via my log as a hacker that someone tried to visit a web page on my URL, but the page that they tried to visit to, I'm actually plugging in at the same time, and I'm stealing that cookie that they would use to go into that page. Remember, like a cookie, sort of like a virtual hand stamp, it's basically just there. It's a bit of information you can present to a server. Rather than me having to log into Skill Builder all the time, you know, every time I want to use it, you end up just going once, you sign in and you say, hey, like, sign in, I've got a cookie, I've got this hand stamp now, and I can present this. Every single time that I open a new tab, or just kind of browse between tabs, every time I present that browser, the cookie, it says, you've already authenticated yourself, you know, in you go. You don't have to do that whole sign-in process again, because that's annoying. So if you've already verified the offense, you know, just have a look at this and you get in. Now, if that cookie gets stolen, which is what this is doing, someone else's cookie, you know, becomes mine. And if I was clever, I could try to use that cookie as my own to become that person's identity. And then I'm suddenly able to log into their bank. I'm suddenly able to get to their profile and act on them, okay? So the trick here is this image here that's going to try to pull some resource from my website. If you know HTML, okay, it doesn't exist. I don't have a list of all the cookies on the website, but I'm being told that someone is trying to access this URL on my site. So the image tag is really just a trick that just forces it to log something from my hack URL, okay? But the idea is that I would be able to steal someone's cookie when they're not actually well defended against this. All right, so there's a couple of tricks that we can do. We don't really necessarily need to be aware of them because I'm going to show you how Web Application Firewall deals with them. What Web Application Firewall will do will sanitize your input, so to speak, all the things that come into your web page. So it turns out that there are things called HTML entities, which again, just other ways of representing characters in HTML. They might be considered special or kind of hack control characters, for example, like left and right. And then it turns out that these can be used to refer to characters instead. So that if I sanitize my input coming through, every time someone literally types out the character left angle, right angle bracket, I would actually just look at that and change it into like less than and greater than. So that if someone ever wrote a greater than character or a right angle character bracket, you change that in the code to ampersand LT and ampersand greater T. Again, this is called command substitution, which is just whatever's responsible for processing this and doing something, it wouldn't literally interpret that. It would actually just display the character left angle bracket or right angle bracket instead, which is one way around this. You can also turn off JavaScript. Like I tried to do this the other day. I was trying to read an article. If you go to here, for example, often you're going to get paywalled after some time. So, for example, there, straight away. But that's because the JavaScript page here, example of that alert function, which just kind of appears on screen. I could disable that. I could go to something like 12foot, which is just a web page that disables that for you. Or you could disable that on your own browser, either way. No, I just go there. Let me just escape. So I'm going to disable the JavaScript. And this would have some upside. There we go. So the browser seems to now be able to show me that web page, which previously wasn't. Why? Because I disabled JavaScript. It does have some upsides, as you can see. But the upside is that we're pretty well defended against cross-site scripting attacks because they're usually just going to be introduced via JavaScript, which you can now disable entirely. But the downside is that JavaScript is pretty convenient, like it's nice. It's for a better user experience. I can't actually get the full. Sometimes there might be parts of your page here that just don't work if completely disabled. So there is trade-offs as well for that. Okay. I'm going to show you an example of. I think these are more examples that we don't need to know necessarily. In the context of a database too, that might work. So we said they might look like this: ID number, username, and password. The obvious vulnerability here is that I shouldn't really be storing any people's passwords like this in the clear. If someone were ever trying to hack this and again get a hold of this database file, that's really, really bad. So we're taking best practices by actually storing the hashes instead, running through a hash function so that when they're actually stored, they get stored looking like this. You have no idea what the original password was because it's a hash. It's irreversible. It's a one-way hash function. So you shouldn't be able to undo what I did when I ran through the hash function. Okay, but we discussed around what happens if they have the same hash. Again, we would introduce a bit of salting in order to change that. The last problem I'm going to show you is what relates to databases is particularly when we see screens like this. This is a very contrived login example that has a username and a password field, like in a find and a forget field. Suppose that if you type in your username, which is the username in this case of alice@example.com, and a forget password at the bottom, and you click login, instead of logging you in, like it's going to email you hopefully a link to reset your password, not your actual password for your, as we previously discussed. But what if when we click on the button, we say, okay, we've emailed you a link to change your password? Does that seem inherently incorrect? Probably not. But what if instead it actually says this? Sorry, no user with the email address. Does that seem problematic when you compare that against with this particular message? So I've mentioned this a few times already. The fact that this message even appears is still another example of information leakage. Again, so perhaps a bad hacker in this case or some other database where folks are not secure with credentials, they have a whole set of email addresses mapped to credentials, like a rainbow table, because human beings tend to reuse the same credentials again on different sites and different servers. So if you're trying different services that you believe users might use, okay, chances are if you have Gmail, you might also have a Google account, you might also have a Twitter account, you might have other things too, which use that same username and password combination. So if this is the way that we handle those forget password inquiries, we're actually revealing some information potentially. If Alice is a user, okay, well, at least we're saying, yeah, Alice is a user of this. She actually does exist. Try this password. Or not, sorry, no user with that email address, then we're not even going to bother trying. Okay, they realize, oh, actually, Alice isn't actually part of the service, or Alice is part of that service. And even if they're not trying to hack into it, we might do something like this because we're also telling the hacker quite a bit about Alice. We're trying to build up a picture around her. So now we know that Alice uses this service, and this one, and maybe not that one. And so you can kind of create a picture as to who Alice might be. they're using her footprint as well just to understand more about her, I think a better response in that case would just be, something like this: request received. If you're on the system, you'll get an email. So that doesn't tip our hand either way as to whether the user is in the database or not. Okay, no information leakage there in that case. Generally, just a better way of understanding your privacy. It's not the only problem you can have with respect to databases, because we've alluded to this idea of cross-site scripting and SQL injection attacks. There's this comment that gets passed around quite a lot when we talk about SQL injection from a webcomic called XKCD. She's great. She sends email letters every Saturday. Basically, this one is a SQL injection attack. Basically, you're providing some information or some text or some query to a database where that query is actually going to do something unintended. Okay, it's SQL itself as opposed to just plugging in some other parameter. So instead of just giving you my name and then searching for the database for that name, I might give you something that is actually a SQL query that's going to be executed on the database, but it's something that you might not want me to execute. Just to see an example of how that might work. Okay, so here's another example of a username in a field. In this case, let's imagine I've written my password poorly and intentionally for the purpose of showing you, so that it actually shows you the type that I've texted out. Okay, as opposed to like showing you stars usually you would like to see, so that no one else should be able to see it. Okay, this is something that someone would be able to see if they visit your website. Perhaps on the back end, like on the server side code, I have what looks like a SQL query that looks a bit like the following. When the login button is pressed, execute the following command. Okay, so select everything from the users table where the username equals username and the password equals password. Now, all we're doing is a SQL query to select everything from the users table where the username equals the username, or whatever they typed in yellow, and the password equals whatever they typed in here in that box too. Okay? And so, for example, if I have someone who's going to log in with the same username, with the username Alice and the password 12345, then the query would actually look like these values going to be plugged into what something might look like this particular query. Okay? If there is no one with the username Alice, or Alice's password is not 12345, then this will fail. Okay? Both of those conditions need to be true. They both need to be true. Yeah? But what about this? What about if someone who's a hacker, okay, or tries to use the username hacker, and the password is one single comma or a single comma one single comma equals single comma one, and it's pretty weird, quite janky. And the reason why this is so weird is because this is an attempt to inject SQL into your database, okay, to trick SQL into doing something that's presumably not intended by the code that we wrote. Okay, so it probably helps to look at it from the inside. Select everything from the users table where the username equals hacker, or excuse me, and basically maybe I do have a person whose username is actually hacker, and maybe that's probably not their password. Okay, that doesn't matter because I'm still going to be able to log in if I have somebody whose username is hacker, and the reason for doing this is maybe because of that or, okay? And so I've kind of short-circuited the end of the SQL query, like word equals, and so on and so forth, okay? So I have this quote mark here at what the end is, what presumably the user has typed in, but I've actually typed in everything in yellow there, okay? That's what I've actually typed into my password to trick SQL to running, okay? Such as that if the hacker's password equals 1, if it literally just happens to be the character 1, then okay, great, I've succeeded. I guess that's a really, really bad password. I shouldn't be able to log in, that way. But maybe that's the case and I'm able to log in. Either way, more likely than not, though, the other thing is true. 1 does equal 1. The world that I live in, at least, that's the case. So as long as someone whose username is hacker exists in the database, which could be the case, I am now able to log in as a hacker because this part is true. This part's probably not true, right? Password's not equal 1. It's unlikely that the password's 1, but regardless of what the actual password is, this part is true. 1 does equal 1. 2 does equal 2. Up is up, down is down. Okay, it's a very, very simple SQL injection attack. I'm basically just logging in as someone who presumably, I'm not supposed to be in the story, but it kind of illustrates the point that could happen. You're allowing people to bypass through. All right, I want you to know you can do all sorts of nasty stuff. I do actually have an example of this, if you'll allow me just a minute. What I'm going to do, folks, is going to get you to run this. Yeah, we can. I'm going to show you very quickly. Okay, let me just open this up. So I'm just going to pull up a bit of code here, which presumably. So we're just simulating again this idea of a SQL injection attack. If I go back to login, yeah, okay. So just to show you how it's kind of difficult to extend this, right? If I've got this file here called login.py, so there's not much going on here, but basically I have this x equals input right at the top. Let me just zoom in somewhat, okay, just to make this a bit clearer to look at. Okay, so if you know your Python, x is a variable, again, and I expect username here, something that's going to prompt the user at the bottom, just with a string username, something that they have to type in, and then expect them to type something after that there too, okay? The result of which the return value is going to be stored here in input. We do exactly the same thing with password down below, except I'm going to store that in a different variable called y. So whatever the username types into the username will be stored in x, whatever they type in the password is going to be stored in y, okay? And then lastly, I'm just going to print, and then in the SQL context, this will be the query that actually gets executed, okay? So, but imagine what's happening instead is select everything, the whole table, the users table, where the username equals, and then the symbol here, this thing there. So what I'm doing here is, so this is what Python calls a formatted string, an F string. That's what the F is doing there. It's not a typo. And that at the beginning just means I'm going to interpolate whatever the person, whatever the user has typed in at their first prompt. That is going to be swapped in to this particular slot there, okay, that F string. And then the second one there, or Y, is going to be this there too, okay? So if I actually run this program, so python.login.py, and it prompts me again, so what's my username? I'll just say Marco, Polo, and then the query, hypothetically, would get executed. And then the way that it would be constructed, if you can imagine inside the database, is like this. Select everything from users, where the username is Marco, and the password is Polo, okay? But if I try to do the thing that the bad person tried to do a moment ago, which is, so let's imagine my username is Marco, but my password is, so 1 equals Or like that, hit enter. Oh, I used the wrong single quote. But notice what I typed in there. Can you see how I kind of left half of it on the left and half of it on the right sort of unsaid? Still though, when I type it up at the bottom, that latter part here, that's kind of true. Let me just run that again. Okay. Sorry. As a password, I'm going to say single quotes. Single quote. Where is it on my keyboard? That's the one. So single quote. No, it'll be one single quote equals, and then one equals one, or that's right. So notice I'm chopping off on the left, I'm chopping off on the right, but when I hit enter, that sort of phrase gets naturally closed. So this is wrong, sure. Okay, password doesn't equal one, but one does equal one. Okay. So that latter part is true. This former part is false, but it's good enough that I would be able to log in if I did something like that. The way that I would get around this is using some fancy trickery. If I use the second file now, where this might solve the problem. Again, it starts exactly the same. So x equals input, y equals something, but now I'm making a pretty basic substitution. Basically, I'm replacing every single time that I see a single quotes with double quotes. Okay. So I'm replacing every instance of the single quotes like I would have done before. I would have to preface it with a backslash because notice when I actually do it, like I'm using single quotes to identify this character. Okay. To kind of close up that thought. So it just happens that I'm indicating to substitute, which is why I'm putting them here in kind of single quotes, double quotes. The thing I'm actually trying to substitute is one single quote. So I want to put a backslash in the front of it just to escape that character so that it actually gets treated as a single quotation mark as opposed to something, some special Python. Python's not going to be able to interpret that in some other way. So if I want to replace every single instance of X here with the double quotes, just replace every single with a quote Y with the double quotes there. Okay. Why would I want to do this? Because in my actual Python string down below, I'm actually using a single quote to kind of offset the variables for the purpose of SQL's interpretation of them. So where the username equals this string, I'm using single quotes to do this, okay? That's single quotes. So if my username and my password are also contained in a single quotation mark character, as might be if you treat your user's input to be malicious, when SQL was interpreting that, it might then think that the next line, the single quote character, is like the end of that too. Well, I'm done with what I prompted. That's exactly how I managed to prompt to trick in the previous example. But let me just show you, okay? So Python login.to.py, and we'll start the same thing, I'll just do Marco. So seems like nothing really has changed, the behavior is otherwise identical. But if I try to do the same behaviors before, so use Marco, but this time, if I just save myself the effort of having to type it out again, copy this, paste it there, hit enter, we'll notice what happened there. Okay, so that's what I'm typing in, but I'm now not subject to the same SQL injection attack because I'm basically trying to select all information from the users table where the username equals Marco and the password equals to, notice that this first single quote there this is the second one. So like I'm now thinking this entire thing from that character to that character is the password. So only if my password is literally one double quotes equal, this and that and this and that, then I would be literally logging in. If that happens to be my password, okay, that would work. But otherwise, I've escaped. I've done a character substitution. I've stopped the hacker from being able to, do the old switcheroo there. Again, so in the defense of SQL, like the substitutions we make are much more complicated than this. Thankfully, at our disposal, we have a service that does just such a thing. I think at that point, it'll be a good point if you would like to try and have a go at the lab. Can I ask you just to get this one going? I think it takes a minute or two just to get going. What I'm going to ask you is, can you press this lab just to initialize it? And I just want to spend 10 minutes talking about what WAF is, now that we've understood a lot of different applications on how we can actually protect our firewall at that level. If that makes sense, let me send this over to you. I think that's the link we want. Do let me know, folks, if that link does take you to the right page. Otherwise, there's the name of the lab. Filtering and blocking web incursions with WAF. Why don't we come back in a few minutes' time? And I just want to take a moment to go over this. Wonderful, wonderful. Okay, perfect. If I had another example here, but I can't quite remember how it works. Let me just see if I can remember. So I know that here. Okay, so let me initialize this one. So I have a server. Imagine this is my website. Oh, I'm at facebook.com. Obviously, it's not facebook.com. I just kind of copied there. I scraped that, I just kind of emulated this idea. It's running locally, as you can see. If I were to type in, so Hacky McHackface, that's my username and password. I think, I've noticed that this could be very simply done with an SSL strip. I could have gone to the wrong place. I press login. The moment I do that, it says, oh, sorry, we can't log you in. My JavaScript, as far as that's concerned, it's a real web page. Like it behaves like I would do normally. Most people wouldn't think about it twice. I certainly wouldn't. Okay. Oh, okay. Maybe it's whatever multitude of reasons. I could even, rather than having a sorry page, actually just redirect them, do something as malicious as just that middle step. What has happened though is at that particular step is, I have captured that information. You see at that server, what I was telling you is that all those logs are going to be captured. Hacky / McHackface, whatever I typed in. There was a post request made at the / login page using those protocols, 200 success. You see what happened is the users who log into that web page thinking it's the actual production web page are not going to the right page, thanks to what I was explaining before. And that even saves it out, captures that to a particular web file. So with Python, it would then save that out to, so capture.txt, which now here, if I open this up, there you go. Okay, at this particular timestamp, that's my information. It's that easy to do, folks. It's not even difficult, okay? I even had like a separate page of that. I think there was one there for like captured. There you go. So they're like all the timestamps. So this is my hacker URL, which you can imagine I'm grabbing all the usernames, all the passwords coming through. How do you protect against this? How do you protect against SQL injection attacks? How do you protect against cross-site scripting attacks? That's what we're going to come back to and see with WAF. All right.